This video is part 2 of our topic, rates of reaction. So in our last video, we discussed factors affecting rate of reactions. Those are surface area of the reactants, concentration of the reactants, temperature, catalysts, and light or pressure, but this is only for some reactions. In this video, we will be going through these 4: surface area, concentration, temperature, and catalyst, and we will discuss in detail how they affect rates, and we will also be discussing some graphs. So the first one was surface area, and in our last video we learned that a greater surface area means there are greater chances of collisions, which will result in a faster rate of reaction. Take, for example, the reaction between limestone and hydrochloric acid. This is the chemical reaction taking place, right? This is the mass before, and this is the final mass. So what we do, we plot a graph of loss of mass versus time. And what we noticed is that limestone, when it is in its powdered state, has a faster rate of reaction, whereas the lumps have a slower rate of reaction. The larger solid particles have a smaller surface area, and the smaller solid particles have a larger surface area. So this graph, it's something that you will be seeing a lot, right? And the key thing here is the shape of the graph. When a graph is more steep than the other, that means the rate is faster. A more shallow graph would mean a slower rate. The next factor we're going to look at is concentration. So let's look at the reaction between sodium thiosulfate and hydrochloric acid. Right, so this produces a pale yellow precipitate which is made out of sulfur. So this is before we add the sodium thiosulfate, and this is after. So the method goes like this. You're going to place some HCl in a conical flask and then add your thiosulfate and begin timing. So very slowly this X will begin to disappear. The solution begins to get opaque as sulfur is being formed. So when you time that, then you repeat the experiment using different concentrations of the thiosulfate, right? So you're using 0.015, 0.0175, and so on. You're just increasing it. Then we will plot a graph of time versus concentration, and then plot another graph of the reciprocal of time versus concentration. This is what your results table should look like. So you have your set concentrations, and you're going to find the time it takes for each one of these for the X to disappear, right? So whatever time you get, then you find the inverse of that. So 1 divided by the time. So say, for example, if you get 110 seconds, then your rate will be 1 over 110, and so on. So this is one of the graphs we will plot based on our results, time versus concentration. For the lowest concentration, it takes the longest for the X to disappear. So if you look here, the lowest concentration was the first one we used, 0.0125, and it took approximately 110 seconds. Gradually increasing the concentration decreases the time the X takes to disappear. So look here, increasing the concentration, it decreases the time. So which means to say, the more concentrated your reactants are, the less time it takes for X to disappear, which means the more concentrated your reactants are, you get a faster rate of reaction. The next graph will be the rate versus concentration. So If you look here, as the concentration increases, the rate of reaction steadily increases. Notice the words that I am using. This is a steady increase. This here is a gradual decrease. They are two very different meanings. Okay? Rate is directly proportional to the concentration. So whenever you see a straight line, that means your variables are directly proportional to each other. In this case, it's rate and concentration. Again, the more concentrated something is, the more successful collisions will take place between reactant molecules. So we're going to look at the same experiment again, but this time we'll actually be changing the manipulated variable. Before, we changed the concentration of the thiosulfate. Now, in this experiment, we're going to change the temperature. So, a fixed volume of HCl is added to sodium thiosulfate at 25 degrees Celsius. Right? So we just do a normal reaction at room temperature and we take down the results. Right? We are going to repeat the experiment using thiosulfate at different temperatures. And then we are going to time it again and plot a graph of time versus temperature. So you have your temperature here and you will be recording your time. So this is our graph of time versus temperature. So again, this shape of graph is familiar to you, right? So this goes to say that the lower temperature means more time for the reaction to take place, right? And here, the higher temperature, which is 60 degrees, means less time for the reaction to take place. What that goes to say is the higher the temperature, the more kinetic energy between the reactant particles. So these particles, the higher the temperature they are moving faster. And the faster something is moving, that means it can bounce into each other or collide into each other faster. Therefore, that will result in the faster rate of reaction. Our next factor is the presence or absence of a catalyst. Take, for example, hydrogen peroxide. This decomposes into water and oxygen very, very slowly. Have you ever noticed in pharmacies, they actually sell hydrogen peroxide in very dark bottles? This is because when the hydrogen peroxide is exposed to light, it breaks down into water. Meaning, if you were to sell hydrogen peroxide in a clear bottle, after a while, you'll just be selling water. So by adding manganese 4 oxide, this reaction speeds up a lot. Firstly, let's look at the reaction setup. So we have our manganese oxide in this flask here. This is our catalyst. And then we are going to slowly add hydrogen peroxide. As the peroxide is added, it decomposes and forms water and oxygen. The water remains in the flask and the oxygen goes through this tube and is collected via downward displacement of water. So it's bubbled here and it pushes down the water. As it pushes down the water, you can measure the volume of oxygen produced. So we're going to repeat this experiment using 2 different amounts of catalyst. The first amount we will use is 1 gram. So using 1 gram of catalyst, right, our graph would look like this one here. 1 gram of manganese oxide will give you a pretty fast rate of reaction. If we repeat the experiment using half the amount of catalyst, you would see here the graph got more shallow, which means that the rate decreased. So the catalyst did speed up the reaction, yes, in both cases. However, more catalyst means a faster reaction, right? So if you look here, catalysts, yes, they do speed up the rate of the reaction. More catalyst gives you faster reaction. they can be recovered chemically unchanged at the end of the reaction, meaning at the end here, this will remain as is, right? And it also lowers activation energy. So if you remember this graph from our last video, the reactants must have a certain amount of energy in order to take part in the reaction in order to form products. What a catalyst does is that it lowers the activation energy so that more reactants can collide and react with each other to form the products. Catalysts are so important in industrial applications. So manufacturers seek to increase their rates of their reactions in order to manufacture a product in minimum time and lowest cost. Usually transition metals act as catalysts for many reactions. So let's say, for example, you come up with a design for a pill, right? Like the pill makes people super smart, right? However, in order for you to produce that pill, that reaction would take place in a month time, right? That is too much. You cannot produce 10 pills in a month. Now, if you were to add a catalyst and you can produce it in a day, that means you'll be able to create more product in less time. Also, maybe if you were to heat it, it would take even less time, maybe half day. So that is some of the things that manufacturers look to do. Always reduce your time and cost to make any product. These are some examples that you will be learning about. So there's iron in the manufacture of ammonia, phosphoric acid, sulfuric acid, manganese oxide, nickel, platinum, and vanadium. All these are transition metals with exception of the acids, right? These are some of the procedures that we'll be going through a little bit lower down in the syllabus. We also have things that slow down reactions. So these are like the opposite of catalysts. They are called inhibitors. Say, for example, enzymes. Enzymes are biological catalysts, right? So sometimes enzyme inhibitors reduces the rate of enzyme activity. Blocking certain enzymes can actually kill different types of pathogens in your body. So a lot of pharmaceutical drugs contain inhibitors. Very interesting fact, I know. So let's summarize what we did today. Increasing temperature makes it more favorable for collisions to occur, hence increases rate. Increasing concentration of reactants means there are more particles in a given volume, which makes collisions more favorable. Increasing surface area increases the available area on which reactant molecules can collide, hence increases rates. A catalyst provides an alternative reaction pathway with lower activation energy. Remember too, a catalyst is not changed in the reaction. Decreasing any of the above will slow down reactions, and inhibitors are negative catalysts, meaning these are things that slow down reactions. Right, so that is it for today. Please look out for a review sheet and we will be going through the questions maybe during class. Okay, that's it for today. Bye.